Now, this film isn't going to be about guns and bullets. It's just that in the last few lessons, we pictured light as if it were a stream of bullets. We found out that to a certain extent, light does behave at least as if it were a stream of particles of some sort. Remember that reflection and refraction, the fact that light moves in straight lines, all seem to fall into place. It's true we've had to make a few extra assumptions here and there, but the picture isn't too bad. Today we'll try to reverse this. Let's take something that the theory suggests, something we know about bullets, and see if it's true about light. What happens when you shoot at a tin can? The bullet doesn't just stop and fall to the ground. For a short time, it exerts an impulse. Now, if light behaves like a stream of bullets, it ought to do something of the same sort. It's not going to send a tin can flying off, but it ought to exert a little push. Let me say it this way. For a theory to be any good, it has to work two ways. It, first of all, has to sum up the things you know, and then it ought to suggest some new experiments to try. So today, we're going to look for the pressure exerted by light. People tried to find this more than 150 years ago, but it wasn't until early in this century that some experiments were worked out that convinced us that we had really seen the pressure of light. Let's try the simplest experiment. I'm going to balance this little mirror on edge and shine the light of a 20-watt automobile spotlight on it. You can see right there the light reflected onto the table, and it doesn't fall over at all. Whereas, if I blow on it just a little bit, over it goes. You weren't in the least surprised at that, because you knew perfectly well that if you turn on the lights in a room, you're not pushed back against the wall, and if you walk out into the sunlight, you don't feel anything pushing on you. You feel a little heat, to be sure, but nothing pushing. So the pressure of light is going to be a little harder to find than that. Let's talk about a more refined experiment. Look at this little pinwheel that I bought at a local drugstore. It's going around in the light of the studio here, and I'll stop it so that you can see it. In fact, I'll do a little better than that. Look here. Here's one I broke apart, and you'll observe that the veins are black on one side and shiny on the other, and that it turns because there's a little, that's soot, there's a little needle point bearing there, and to be sure it's blowing around, it has to be encased, and as a matter of fact, it has to be evacuated in order to do that, and the pressure in there is only about 1/millionth of an atmosphere. It was invented more than 100 years ago by Sir William Crookes in order to demonstrate the pressure of light. We call it now the Crookes radiometer. Let's take a look at how Crookes reasoned this thing out. Here is the needle point bearing there, and here are the 4 veins, and here are the sooty sides, like that. Now, Crookes said that if a particle of light hit here, on the black side it would be absorbed, whereas if a particle of light hit here and is reflected back, there would be a larger push on this side than on this side. We can measure this effect. Here's an ordinary steel plate hung from a wire so that it swings this way. And at the top of this steel plate on this side, I have a little axle grease to act as an absorber for bullets. And the bottom of the steel plate is clean, so it's a reflector for bullets. Let's try a very simple experiment of comparing what happens to the turning of that steel plate when I hit the grease and when I hit the plain steel, and it's reflected. I'll first mark a 0. That's where the edge of this little marker is. Now, I should hit the grease, and the little marker moves this far. So, and let's try now once more. Same size bullet. This time we'll hit the steel down at the bottom. And the marker moved almost twice as far. You can try that experiment yourself sometime. Just take a kitchen frying pan, maybe that big, a heavy iron frying pan, and instead of using that axle grease, use a little butter. It's easier to wash off, and any kind of thing like a pistol and ball. I think you'll find that if you do it repeatedly, that the push that the plate got when it reflected the ball back was twice as big as the push it got when it absorbed it. And that is what was Sir William Crookes thought was happening in the radiometer. Let's take a look at this. If light behaves like particles, it's going to exert twice as much force on the shiny side, that side, as it does on the black side where it's absorbed. And so it ought to go around. Let me put a good one there in the field of view. You can see it going around in the studio lights. And in fact, if I bring up my 20-watt lamp and shine it on it, it just whizzes around. But let's look at this a little more closely. According to our theory, the push should be greater on the shiny side than on the black side. There you see it going around, and it's going around with the black side trailing. So it's wrong. Something's the matter. Something doesn't add up. And that's exactly what Crookes thought when he invented this device. Now, nature isn't wrong. The theory's wrong. Instead of demonstrating the pressure of light, he must have been demonstrating something else. So Crookes, who had set out to solve one problem, ended up with two problems. He was convinced that light must exert a pressure, but clearly he hadn't proved it. And secondly, he now had to find out what made the pinwheel go backwards. A man named Sir Arthur Schuster reasoned that even though most of the air had been removed from the glass bulb, it was still the remaining gas inside, the gas inside, that was responsible for this funny misbehavior. He was able to prove this, and I think we can too. Let's take a look over here at what I choose to call a homemade radiometer. You'll see that we've tried to make something like the one you've seen just a moment ago. It's a little fancier than that. Over here is an electronic vacuum gauge. Down below is a pump. It's an electronic pump, too, made for this kind of operation. Just above it is a steel ball in a seat, so arranged that if I lift the steel ball out here and bring it over to this part of the glass tubing, it will open up the tube here and allow the pump to pull the gas out of the radiometer down into this region. Let's turn on the gauge. Can I have a little help? The gauge is beginning to read. Okay. The pressure reads about 4/millionths of an atmosphere. Now let me bring up my light again. You can see the vanes go round. Now let's see what happens if we try to improve the vacuum. I'll lift the ball valve out of its seat there. The vacuum is improving. I don't know how low it is, but it's pretty low. Now let's shine the light on it. And there the light is shining on that vein. It shines on this one. It shines on that one. But it certainly is not an effect. What we see there is that if there's no gas, there's no go. In other words, the Crookes radiometer is something that's working by gas pressure. And if we can see that the gas is needed to make the radiometer work at all, it must be the gas that's making it go backwards, at least backwards according to the theory. A complete explanation of this is pretty complicated, but I think we can understand it in some kind of way like this. Suppose we picture the radiometer as we did before, with the sooty sides, the black sides here. So, now, the gas molecules hit black sides and hit shiny sides. The effect of the light is to warm up the black side more than it does the shiny side, so that a molecule that comes down here and hits this and then goes away again goes a little faster than a similar one coming at the vein from this side going this way. The recoil, therefore, is greater, and that means that the push is predominantly on the black side. In other words, it should move from the gas inside the vessel with the black side trailing. And that's, in fact, exactly what the radiometer does. So we come to another question. The other question is, has the radiometer failed to move because there is no pressure of light? Or has the radiometer failed us because friction at the bearing or something of this sort? To find out, let's use a more delicate piece of apparatus than any we've used so far. Here we have one made specially for this purpose. Supported from the top is a very thin fiber drawn from molten quartz. It's about 1/10 the diameter of a human hair. You might be able to see it jiggling in there. I just barely can see it. Suspended from the end of it, right down here, is a small piece of aluminum foil cut from a kitchen foil, thin kitchen foil. It's just hanging from the bottom there. And down here is another one of those electronic pumps that keeps this vessel, this piece of glassware, evacuated better than anything that we used before. Now, you'll see that this experiment is specifically designed to get rid of the effects that were interfering with the others. We get rid of the friction by suspending a light vein on a very fine thread. We get rid of the trouble caused by the gas in actually 3 ways. First, the vein is so thin that the temperature will equalize on both sides in a very short time. It's as hot on one side as it is on the other. Second, the vein is shiny on both sides, so there won't be any uneven heating. And then third, and of course most important, the vacuum is so good that the effect of the residual gas is really completely negligible. The calculation of that effect is in the film notes. It's a little laborious to go through right here. Now let's try the experiment. I'll pick up our old friend, this lamp, and carefully shine that on one side, and you don't see anything much happening. Well, it moved a little bit, but it's not very convincing. Let's try another trick. Let me shine this light first right there, And when it's swinging away, I'll shine it again. There. I'll shine it on that side again. Once more. I'm pushing all ways on this side when it's swinging away. You heard me say I'm pushing. I shine the light on this side, and the light's doing the pushing. There are not many people in the world who've seen that thing and know that they've seen the pressure of light for sure. It's a small effect, but there it is. Now, this is not just an experiment to see whether the pressure of light exists. We can also measure the pressure of light this way. If you measure the time of the swings, that is, the number of pushes you have to make to swing it up to a certain amplitude, and if you know the mass and size of that little vein there, you can calculate the pressure of light quite directly. And if you do it with this particular apparatus, you get one which is in a quite good agreement with everyone else's determination of about 10 to the minus 9th atmospheres from that 20-watt lamp. Now, that's a fairly small pressure. On the other hand, you may want to know, how does that compare with other light intensities that you're used to? If you walk out into sunlight, the pressure is about 1/30th of that. It's about 3 times 10 to the minus 11 atmospheres. The reason our pressure is larger than the one in sunlight is because we've concentrated that light with a lens so that, in fact, it almost burns my finger. It's only natural now to ask whether something that's as small an effect as that has any role in the universe. The tail of every comet, for example, streams away from the sun. It doesn't follow the comet. And it was just this effect that suggested to Kepler, as early as 1619, that light had pressure, and he began to look for it. How much of this is actually due to light pressure and how much is due to other effects like streams of other particles, we don't exactly know yet. The astronomers don't quite agree. But light pressure plays a part. But it plays an even greater part, and this for certain, in the stars. It's the pressure of light that keeps many of them as large as they are. You'll find the detail of this in the film notes. Now, if you'll pardon my being a little corny here, I'd like to say it this way. Here we've seen something which was almost completely trivial. We had to make a very fancy apparatus to see it. Nonetheless, it is one of the major building blocks of the universe. It keeps the stars, and that's where most of the mass is, it keeps the stars out to the size that they are. Now, let's review a little what we've done. We've had a theory that light was a stream of particles, sort of like bullets. We know that when bullets strike an object, they exert a momentary force. And so we reasoned that if the bullet theory of light is a good one, then a beam of light should push on any object that it strikes. And then, after some difficulties, we found that light does exert a force, and so the bullet theory does indeed predict the correct behavior of light. Now, what have we done? We've given strength to the bullet theory, but we haven't proved the bullet theory. In fact, we're going to find presently that a wave theory of light also predicts a pressure. But more of that later on.
order random events is number effect indeed. Can that large be overall of events are very events? No, of predictable, which such the occur with yet very unpredictably.
Dr. Hume just told you what this film is about. He wrote a sentence to explain what we want to show you. And then he cut the sentence up into individual words, put the slips of paper into a hat, and drew them out in a random order, and read them to you in this random order. Here's the sentence before it was scrambled. Random events are events which occur with no order, that is, unpredictably. And yet, the overall effect of a very large number of such events can be very predictable indeed. Who's going to start?
Well, let's use a random event to decide. Heads or tails?
Tails.
Heads, you lose, you start.
Here are random events occurring naturally. See the needle? Hear the clicks? This is a Geiger counter, and this contains a radioactive material, polonium. Every time the Geiger counter clicks, it means that an atom of polonium has changed into an atom of lead, except that there are some extra clicks because of cosmic rays. I said that these clicks are random events. What does that mean? It means that there's no order to them. I can't predict when the next one will occur. Even if I measure the time between clicks very accurately for a large number of clicks, I will still not be able to predict when the next one will occur. That's what I mean by a random event.
Here's a picture from your textbook. A graph of the activity of a sample of polonium plotted against time in days. You can see that the activity, that is the number of radioactive disintegrations in the sample, decreases as time goes on. The activity at the start is 100%. It's only 1/2 as much at the end of 138 days. At the end of another 138 days, it's half of what it was at the end of the first 138 days. It's down to 1/4 of its original activity. And this goes on. Every 138 days sees the activity cut in half. This length of time is called the half-life of polonium. All radioactive substances behave in this same way. Some have very short half-lives. Here's helium-6, a radioactive isotope of helium. It has a half-life of 0.8 of a second. Some have very long half-lives. Here's uranium-238. Its half-life is 4.5 billion years. As you can see, if a graph of activity is plotted in terms of half-lifetimes, it is identical for all radioactive substances. This is a law of radioactive disintegration, a description which fits the behavior of a great variety of substances and allows us to predict their activity at any time in the future. How can this predictable behavior emerge from the random, unpredictable behavior that Dr. Ivy showed you? Well, we'll come back to radioactivity later, but first we're going to investigate some other examples of random behavior.
Would you care to predict where the next marble will go? The same place? No. I'll try a few more. Unpredictable, isn't it? There are 100 marbles in here. I'll drop them all. in here. Maybe that's the slot that the marbles are most likely to go into. I'll mark the way that the marbles are distributed here. I'll put the marbles back in the tube. Now I'll do it again. You can see that the distribution is not going to be the same. This time, there are most marbles in this slot. Perhaps now I might guess that the marbles are more likely to go into the slots here, but that's all it would be, a guess. I still haven't made enough observations of the behavior of this apparatus to make reasonable predictions about what will happen. So I'm going to take some statistics on the apparatus. That is, I'm going to observe what the behavior is in a systematic way. I'm going to drop 100 marbles many times, and each time draw a graph like this of the distribution. And Dr. Hume will help.
Well, let's get to work. Here are the 10 distributions we found in 10 tries. You can see that they're all different.
I'll put 3 of them together so you can compare them. Now you can see the sort of fluctuations that there are between them. This graph shows the next thing that we did. We added together these 10 distributions, and we divided by 10 to make this graph the same size as these graphs. This is now the average distribution for the 10 tries. One way of looking at this is that this is the distribution we would have found if we dropped 1,000 marbles all at once in the apparatus, except that we couldn't because the apparatus won't hold 1,000 marbles all at once. Then we did this again. Dropped 100 marbles 10 times, and got another 1,000 marble distribution, and once more. There it is. These 3 are 100 marble distributions, and these 3 are 1,000 marble distributions. You can see that the fluctuations here are much smaller than the fluctuations here. If we dropped 1,000,000 marbles at a time in the apparatus, then we probably wouldn't be able to see any fluctuations at all. Each of these graphs is a frequency distribution. And the point of taking a lot of statistics for the apparatus is to get the best approximation that we can to the true frequency distribution for the apparatus. The average of these 3 will be reasonably close to the true frequency distribution. Here it is, the average. Now that I have this, I can make predictions, statistical predictions, about the behavior of this apparatus. You can see that the frequency here is about twice that of the frequency here. This means that the probability of a marble going in this slot is about twice that of a marble going in this slot. It didn't go in either one. You must realize that a single marble still behaves unpredictably. To say that the probability of a marble going in here is twice that of a marble going in here just means that if I drop a very large number of marbles, twice as many of them will go in here as go in here. And as you've seen, very large number means just that.
You've seen how to find the frequency distribution for a simple pinball machine. What about this machine? It has 16 squares of cardboard mounted so that they can spin around. One face is white and the other face black. Now the light scattered from these squares can be read on a light meter over there, and the results projected on the screen. Right now, half of the squares are white and half of them are black, and the reading is 8. Now Dr. Ivy is going to turn the squares around so that they are all white side out.
Now?
Yes, now. We've made the scale on the meter so that it reads directly the number of white squares facing out. And the reading now is 16. Now we better check up on the all black reading. The reading is 0, no white squares facing out. Dr. Ivy is going to start the squares spinning now with a fan. He has to help some of them along by hand. I want them to end up facing out, so he's sliding a screen across the back. The reading is 8. Now we're going to do this again several times and just show you the results. You might expect that the most probable result would be 8, corresponding to half black and half white. But we get considerable fluctuation from this. 6. Well, we'll have to do this a large number of times in order to get a proper frequency distribution.
I don't think I have the strength.
Well, don't worry about that, because for this machine, I can calculate the frequency distribution. I'll show you. When I spin one of these cards around, it comes out either black or white, and I can't predict which. I can't see any reason why it should come up white instead of black. So first of all, I assume that these two alternatives are equally probable. Now these squares spin quite independently of each other, so the final result is the overall effect of 16 independent random events. How do I calculate the probabilities of the 17 different possible results? There's only one way to get all black or all white, so these two meter readings are equally probable. And they're certainly not very probable. But look at the arrangement of squares right now. The probability of this particular arrangement is exactly the same as that for all black or all white. But the meter reads the overall effect and can't tell the difference between this arrangement and any other with 10 white and 6 black. So the probability of a particular meter reading depends on the number of different ways the reading can be produced. There are 16 different ways of getting 1 white or 1 black. So these two meter readings are equally probable and 16 times more probable than this. You may be able to go on now and calculate how many different ways there are of getting 2 white or 2 black. There are 120 different ways. Now, I'm already off scale here, but I plotted this frequency distribution before, and here it is, to a much reduced scale. You can see that the ones that I was calculating before hardly show here at all, and that the 8 is the most probable. Perhaps you can try working this out for yourself. But you must remember that when you do make a calculation of this sort, that you should do experiments to check it. Now over here, I have a similar machine with spinning squares. Here, there are 256 cards in the same area. The overall effect of this one is made up of a much larger number of independent random events. What about a frequency distribution for it? For 16 cards, a reading of 8 is more probable than the others. For 256 cards, a reading of 8 is very much more probable than any other reading. In fact, it is so much so that I can almost say with certainty what the result will be when I spin the cards. I predict a reading of 8. Let's try it. It checks my prediction. Let's do it again. Eight. Eight. Eight again. The fluctuations are very much smaller here. This reading is predictable. That's why we said in the beginning that the overall effect of a large number of random events is very predictable. Now, at last, we're in a better position to talk about this law of radioactive decay that we started with. First of all, what does it mean to talk about activity? It should mean that a sample of radioactive material has a definite, predictable number of disintegrations in a certain length of time.
How can Dr. Hume speak of a predictable number of disintegrations in a certain length of time when the disintegrations are random? I'll show you with this. It's a Geiger counter which displays the number of counts here. I'll start it. 1, 2, 3, 4, 5. As you can see, the time between counts is not predictable. When there are 10 counts, then a 1 comes up in the tens column, and the unit column starts over. Now I'm going to move the radioactive polonium here closer to the detector. This will increase the number of counts. The unit column is still random, but much faster than before. The tens column is pretty random, but watch the hundreds column. 600, 700, 800, 900. These are quite regular. There is some fluctuation. This fluctuation would be even smaller if I took 1,000 counts at a time. This is just the law of large numbers. I can never say what the time interval between single counts will be, but I can say fairly accurately what the time interval for a large number of counts will be.
Well, that's how we get the activity to plot on this graph. Now, why does the activity decrease in this particular way for all radioactive substances? This, too, fits the idea that disintegrations are random events. Perhaps I can simulate this behavior with a sort of game. Here are 60 dice. Think of them as atoms, a rather small sample compared to the vast numbers of atoms in any piece of radioactive material. Suppose that the 5s represent atoms that have just disintegrated. I'll pile them up here. The chance of a 5 turning up is just the same as any other number. It happens at random and is independent of what comes up on any of the other dice. These represent the activity in the time interval of the first throw. They are no longer the same atoms they were before they disintegrated, so that they are eliminated from now on. Now I'll throw again. The chance of any one of these dice coming up 5 is exactly the same as it was on the last throw. I'm piling these up beside the first row. This time there are fewer atoms disintegrating. There's one more. Now, I'm going to go on doing this throw after throw, and you'll see what I get. Next row. I still have a few dice left that I'm trying to get 5s with, but I'll stop here. This is an activity time graph for this dice game, and I want you to compare it with the activity graph for a radioactive substance. The dice graph isn't smooth. There are sizable fluctuations which are bound to occur because I had only a small number of dice. But the general trend is exactly the same for both. So it looks as if the law of radioactive disintegration is the same as the law of chance for these dice. I mentioned the law of chance for the dice, but I'd better say it again. The chance of any one of the dice turning up 5 is exactly the same on every throw. This means that the chance of an atom exploding in any one time interval is the same as in any other. It doesn't change whatever as time goes on. atoms, unlike people, do not have a greater chance of disintegrating as they get older. The chance always stays the same. Perhaps you can calculate for yourself what the half-life of these dice should be. From this experiment, it looks as though it is about 4 throws.
So far, we've used one particular natural phenomenon, radioactivity, to illustrate random events. That's because the random nature of the individual disintegrations is apparent. Orderly behavior is observed for a radioactive substance only if the time for a large number of counts is used as a measure of activity. Now, you observe orderly behavior in the measurements that you make. For instance, you measure light intensity with a light meter. The needle doesn't jump around in an unpredictable way. Does the orderly behavior that you observe always arise because of random events? This question can only be answered by doing experiments, many experiments. These show that sometimes the order that we observe does have at the roots randomness which is not apparent. But this isn't always true. Sometimes experimental results indicate some sort of order at the roots.
How can we tell when randomness underlies orderly behavior? Here is orderly behavior. Every time these squares spun around, the reading was 8. It's clear that the order here comes from randomness, but I could not tell by watching the meter alone that this was true. Now suppose that I masked off all of the squares here except 16. The light going to the meter would decrease, and I'd have to use a more sensitive meter. But the point of this is that I could then tell by watching the meter alone that there was randomness. It would be just like the machine with 16 squares. There would be observable fluctuations.
You know that very large numbers of photons arriving at a light meter produce the reading. Is the arrival of a photon a random event? To tell this, it would be necessary to cut the number of photons arriving at the meter down to a much smaller number, and of course, use a much more sensitive detector. Experiments like this have been done. This film shows an oscilloscope which is connected to a very sensitive light detector. You can see the pips caused by the arrival of individual photons, and you can see from the intervals between them that there is evidence of randomness. We see order in the world around us, order that enables us to make measurements. For instance, measurements of light intensity with a light meter. Often, this order arises from random events, such large numbers of random events that the most probable thing is the thing we always observe.
I've made it look as if I were going to write a definition of time. But the fact is I can't, nor can anyone else. If you look up time in a dictionary, you'll find that the definition contains words like succession, event, before and after, words that already contain the notion of time. I can define a watch. There's no problem there. But I can't define time. And this reflects the subtlety of this notion that we all take for granted. Still, there's no use pretending that we don't know what time is. For instance, 1 second is a reasonable time. Your heart is beating perhaps once a second. And on the long side, 100 years is certainly an extreme. You perhaps can't live that long. Now, what about shorter intervals down in this region? Well, this movie that you're seeing is made up of many individual still pictures. And my gestures seem perfectly smooth, but if we slow up the camera so that there are fewer frames per second, your eye and brain now begin to distinguish individual frames, and the motion of my hand seems jerky. Here you see the usual still picture at about 1/12 of a second instead of the usual 1/24. Now let's look at it for about 1/6 of a second. Here we are showing only 6 different still pictures a second, and it has become definitely uneven. So you see that our ability to distinguish short time intervals falls somewhere between 0.01 and 0.1 seconds. There are some experiments that you can do yourself that check this sort of thing that are described in the film notes. Now, what about all of these shorter times here that we can't appreciate directly? There are a variety of ways that we can use to expand our time scale and find out what happens. Here's a picture of drops splashing into a cup of milk. Now let's take one of these and examine the pictures the camera took one by one. This is some idea of what we see, but it doesn't tell us very much. Now let us imagine that here are some of the pictures that we just saw. They are separated in time by about 1/24 of a second and about this much on the film itself. Suppose that we had a high-speed motion picture camera that took many thousands of pictures during 1/24 of a second. Then the film would be longer, and by looking at these pictures, we would be able to see just what happened in between the pictures that we have already looked at. It seems quite unbelievable in a way, and yet the milk drop does get into the cup with some kind of splash. It gets from the state in which we first saw it to the final state by a series of continuous processes. Now, we're never going to be able to observe directly what happens in these very short time intervals, and yet we feel that this technique we have of expanding our time scale and looking is perfectly legitimate, yet we can't prove it. And this is another example of the subtlety of time. Now, just for fun, I can take something that takes place in a long time and squeeze it down, telescope it, so it takes place in a short time. Here is a rose, and it's growing, but nothing seems to be happening. You can watch it for 5 minutes, and then you get bored. But if we take a picture once an hour and show them rapidly like this, you can see the flower unfolding in an almost explosive way. Now I'd like you to notice something about these 2 sets of pictures we've just looked at. They each contained a clock. In the case of the unfolding rose, the clock was just an ordinary clock. And in the case of the splashing drop, the clock was just the shaft on a little motor which was turning at 1800 RPM and which had a mark on it. Now this is the essence of all time measurements. One compares the start and finish of an event with the position of a clock's hands. Now let us talk some more about clocks. A clock is a device that makes regular events. For instance, it could ring a bell or flash a light, or the hands can move by in front of a face. Now, there's no trouble with those events, but the difficulty is to know what perfect regularity or what even ordinary regularity means. Now, what do we mean by regular intervals of time? That's kind of hard to test. We have to compare one clock with other clocks and keep doing it. It's fortunate that we have a tremendous body of evidence that tells us our clocks aren't off much. We don't notice any serious discrepancies, a minute a year perhaps or less. But when we get down into higher precisions, we need better standards. Now, a well-isolated standard that has been used for a long time is the solar system. here's a sketch of the solar system for our purposes. It has the sun in the middle, the Earth, say, here, and the moon going around the Earth, and planets are moving around here. Now, for centuries, we've observed night and day as the Earth turned around its axis, and the moon, the phases of the moon have been observed from month to month, and the seasons themselves, and these all serve as approximate clocks. Nowadays, we use much the same motions, but we observe in a much more refined way with telescopes, and then we still find that the motions are not very regular because they're all influencing each other. And in fact, the second, which is defined as a certain big fraction of a particular year, is not really very conveniently reproduced by this sort of standard. So we either need a quicker standard of time or convenient ways of subdividing time. Now, one way of doing this that's crude and convenient is to use one's pulse. And I can tell you an interesting story about Galileo, who was watching a lamp swinging in a church and timed it using his pulse. Here's a bowling ball suspended from the ceiling of the studio, which is about 25 feet high. Let's imagine that it's a lamp, such as Galileo might have observed in a church. And he found that whether it was swinging in a big arc like this, or a relatively small arc such as this, that it took the same time, as he found by timing it with his pulse. Galileo also found that the period of a pendulum depended on its length. Here's the pendulum, and it's taking a certain time to swing. If I shorten it, it swings faster. If I shorten it still further, it swings even faster. Not much else affects the time of a pendulum. Now, here are three lamps, or rather bowling balls, a little one over there and a big one here, held up by strings, and another little one here, also held up by a string, and much further up. And when I burn the threads, they will all be released nearly at once, and they should swing together. Now, let's try this experiment. You will see that Galileo's statement is certainly right, at least if he was just timing it with his pulse. And in fact, the pendulum makes a remarkably good regulator for clocks. And how would you check it? Well, you'd compare several of them together, just as we're doing now. So the pendulum became the standard device for dividing up long intervals of time. Now, here's a pendulum clock whose pendulum is arranged to beat seconds. In this way, we can easily compare the time told by a clock like this with astronomical time. These clocks have been refined to a high degree, but they're still not good enough. They're not isolated well enough. If the weather gets warmer, the pendulum gets longer and the clock gets off. If one takes it up on top of a mountain, the force of gravity is different, and the clock will also not tell the right time. We can make clocks with atoms now, and we have learned to do this since the Second World War. Here is an atomic clock, one of a couple of dozen in the world. It uses the vibration of cesium atoms to control its output, which is down here. The front half of this apparatus consists entirely of electronic equipment, this kind of thing. In the back is the apparatus that contains the cesium atomic beam. Here is the part of the atomic clock that has the cesium in it. The cesium atoms start down here and travel up through this little tube, vibrating as they go, and eventually strike a detector. As you can see, you don't see very much. Now, what sort of evidence do we have that cesium clocks keep good time? You will remember that when we wanted to tell whether a clock was regular, we compared two of them. And this has been done with cesium clocks. Here's some data that show how they perform. This is a curve of the difference in frequency of two cesium clocks over a 3-day period. Here's 1 day, 2 days, 3 days. And let's see, the height of each of these boxes is 2 parts in 10 to the 11th. So you'll see that over a 3-day period, these two cesium clocks didn't differ in frequency by more than about a few parts in 10 to the 11th at most. Now, how much is a part in 10 to the 11th? Well, there are 30 million seconds in a year, so that in 3,000 years, we would have about 10 to the 11th second. So that 1 part in 10 to the 11th is 1 second out of 3,000 years, and that's the sort of discrepancy that would arise between two cesium clocks had they been running for 3,000 years. Now, it would seem that cesium clocks agreed with each other, and in fact, they work so well that they may become our standard of time instead of using astronomy the way we do now. It's a good question to ask whether cesium clocks would keep the same time as astronomy does, and experiments are now being done to find this out. We don't yet know what the answer is, but if there is a discrepancy, it might throw some additional light on the fundamental nature of time. For many purposes, we don't need the precision that is available from an atomic clock, but we do want to observe events that happen in short time intervals. And one way of doing this is to use high-speed motion picture photography. Professor Harold Edgerton has developed this technique to a high degree, and he will now tell you something about how it works and the way he uses it.
We are now in the stroboscopic light laboratory at MIT. Here we study events which happen in a very short interval of time. To do this, we use electronic flashlights and various sorts of cameras that are associated with these lights. At the right here is one of the lamps that you will shortly see in action. In an ordinary motion picture camera, the film goes through at 24 pictures per second. In this camera, it goes through at a rate of many thousands. Then when the pictures are shown on the screen at the normal rate, you see the motion greatly reduced in speed. I'm now going to show you the stroboscopic light. Each flash of light lasts approximately 1/millionth of a second. I will now run it several times a second so that you can see it glow. To your eye, it looks as though it were continuous light when it is running at these very high speeds. I now wish to show you an example of how high-speed photography can slow down very rapid motions. Consider as an example this balloon. You are going to see this balloon broken with a camera running at normal speed. Everything happened instantaneously before your eye. The balloon in one picture was complete. In the next frame, it was collapsed. With the high-speed pictures, you will be able to see what happens when the knife breaks the balloon. I will now show you some examples of the usefulness of such pictures. This picture shows smoke flowing through the blades of an electric fan. The slow motions permit us to study these currents and to understand how they are formed. Pictures like these help us study how a bird flies. Actually, we seldom use high-speed motion picture techniques in studying rapid motions. Instead, we use simpler techniques involving single pictures or even double pictures taken at exact times. This one example shows a bullet in flight, and here you see two pictures of the same bullet, which are taken 100 microseconds apart. In other words, the light that took this picture took one flash, 1/millionth of a second, and then the second flash occurred 1/10,000th of a second later. The examples that you have seen were taken with exposures down to approximately 1/20th of a microsecond. Beyond this speed, it is almost impossible to get pictures because of the dimness of the light or the insensitivity of the film.
Frequently, we don't need the detail of a photograph, and all we have is an electrical signal. Now, microphones put out an electrical signal from sound, and photoelectric cells put out an electrical signal when light strikes them. And there's a whole host of devices of this sort. So how do we study electrical signals? Well, we use a cathode ray oscilloscope. Here are two of them. Now, this is a very useful one that you could build yourself from the kit. And here is a considerably more complicated and elaborate instrument. These devices are so useful that it's worth taking some time to talk about their operation a little. This tube here is very much like the tube in the television set. A bright spot travels back and forth. Here it is. And when I apply voltages to the scope, like this, I can make the spot go up or down at will. I can also make it go sideways like this. And in fact, the scope itself makes the spot go sideways. It'll move from the left to the right at a slow rate and then come rapidly back. Watch. Now, if while it's doing this, I apply a voltage, an electrical signal, you will notice that the thing will go up, stay up, and come down when I stop, or alternatively, it'll do that, and so on. In this way, I can see what happened during the time that the spot is traveling across the scope face. Now, you'll notice that it's taking a couple of seconds for the spot to get across the screen here. I can speed this up a lot. Here it's going 10 times faster, and here it's going 100 times faster. When it's going at that rate, it's logical to look at a common phenomenon, namely the AC power line. Let me connect the AC power line to this scope, like this, and plug it in here. Now we see what the power line looks like on a cathode ray oscilloscope. If I count the little boxes from here to here and read all these dials, I can figure out that it takes a 60th of a second for the spot to go from here to here, which is just what it should be. Now let me show you something. Here is a pendulum which is equipped with a brush that writes on this piece of paper. Now, if I set it swinging like this, and then pull the paper down at as steady a rate as I can manage, I get a trace of the motion of the pendulum plotted against time. If this distance from here to here represents the period of the pendulum, so is this the period of the pendulum from here to here, from any corresponding point. And this is just the same sort of curve that we have on our cathode ray oscilloscope right now. Many phenomena look like this, many vibrations. Now, if I wanted to continue having this plot, I'd have to keep on pulling out paper. The cathode ray oscilloscope gets around this by using the same piece of paper over and over again, so to speak. After it's got this far, it comes back and retraces the same curve. Now, instead of using our cathode ray oscilloscope to look at something that repeats all the time, like the power line, let's put in some signals that occur just once, and, for instance, a flash bulb, and see how long a time it takes for a flash bulb to flash. To do this, I connect up a photoelectric cell of this sort. You can buy one of these for $2 or so at your local radio supply house, and here it's connected up to a battery and so on. Now let me connect it to the scope. This. Here. And now you see, if I make some adjustments here so that I can pick up the lights from the studio, there's a little opening here. I've covered it with tape so as not to put too much light in. And here's a little opening, and you can see as I move it around, I'm picking up the studio lights here. And when I put my hand over it, the spot goes down. So the more light I let in, the higher the spot is. And if I put my fingers across here in rapid succession, you can even see 4 little wiggles. Now let's use this with a flash gun. I'll put it here, and I've predetermined roughly where this should be set here. And I'll also speed the sweep up a little to be about right, and it usually takes quite a few tries before you get the scope adjusted so it does just what you want. And now that I think would be about right. And now here's a flash gun, and I'll put that about here. And I'll connect up 2 wires. A remarkably unstable arrangement. And now I'll set it off. There, I think you can see this pulse that occurred here. Let's do it again. Now let's stop the film and look at this image. You see that it occupies about 2 boxes here, and since there's, by reading these dials, I know it's 50 milliseconds per box. It takes about 1/10 of a second for this flash to be over. Now that's not very fast, and it would be interesting for you, using a much simpler scope, to compare that with a strobe, which gives a much shorter flash. Now with cathode ray oscilloscopes, we can measure times as short as 10 to the minus 8 seconds, and with very special ones, one can get down to 10 to the minus 9th seconds. Now, one can go further. One can use coincidence techniques to measure intervals that are as short as 10 to the minus 10th seconds, or thereabouts. Suppose 2 pulses occur in time, like this. One can delay the first one until it sits on top of the second. And by measuring the delay time, which one can do in terms of the length of a cable, one can get down to the vicinity of 10 to the minus 10th. And that's about as far as we can go with electronic techniques. Now, still shorter times can be measured and can be observed by allowing particles to make their own tracks in film, this kind of picture, like this. Such particles often travel with very high velocities, such as pretty close to the velocity of light, which is this. So if one can, using one's microscope, one can look at the film, one can measure distances that are as small as, say, 3 times 10 to the minus 5th centimeters. And since the velocity is this of the particle, the time that it took the particle to traverse the little track is of the order of about 10 to the minus 15th seconds. You can see that this is not as direct a measurement as either of these sorts. One is inferring this from looking at the track. Now, one can imagine shorter times still. After all, light can cross an atom. And how long does that take? Well, an atom has a diameter of about 3 times 10 to the minus 8 centimeters. And again, light has that velocity. So that the time it takes light to cross an atom is about 10 to the minus 18 seconds. And now if we consider a nucleus, we get to even shorter times. A nucleus has a diameter of around 10 to the minus 13 centimeters, and now the time for light to cross a nucleus would be 10 to the minus 22 seconds. Imagine them, and of course one can talk about them, and we're not sure just what they mean. And in fact, nobody knows. And it may be that time of these short intervals cannot be thought of the way we've been thinking of it when it was measured in longer intervals. It's just rather like matter. If you have, say, some material such as gold, and you divide it and keep on dividing, you eventually reach one atom. You can't imagine this anyway, and now you can't divide any further and still have gold. Perhaps time is like that, and one just can't go on to arbitrarily small intervals and have time as we think we understand it. Now, where are we? Well, first we started talking about time, and we were a little bit vague about what time really meant, because we couldn't help it. And we talked about those intervals that we could appreciate directly, and how we measured them, how we set up clocks and standards. Then we went on to shorter intervals, time intervals where we either had to use photography or cathode ray oscilloscopes to see what was happening. And then we got less and less definite and went to even shorter times, and finally we got to a point where we can't observe anything and where we just talk. Now in the next movie, we're going to talk about longer time intervals and see what happens as one goes towards billions of years.
This is Francis Bitter's Magnet Laboratory at MIT. We're fortunate enough to be able to use some of the apparatus here for our demonstrations of magnetic forces. You're all familiar with electromagnets. They consist basically of a coil of wire through which a current passes, producing a magnetic field, like the electromagnet in this doorbell buzzer here. Now, the current requirements of this electromagnet are quite small and can easily be supplied through light wire, like this lamp cord here. The electromagnets in the magnet laboratory are basically the same. They consist of coils through which currents pass, producing magnetic fields. For most of the problems studied in this laboratory, strong magnetic fields are needed, so that the currents through these coils have to be very, very large, and the coils have to be cooled by hundreds of gallons of water a minute. The very large currents, 10,000 amperes or so, reach the magnets through these bus bars overhead, like the one Dr. Bitter will show you over there.
Here we have the bus bars that carry the current around the laboratory and can be fed through switches to any one of several magnets, like the one here. If you close this knife switch, like this, to carry the current on to the heavy leads here coming to the magnet. Here, the terminal which brings in the current is connected to a smaller coil which goes from this plate to this one, out of this electrode, out of this bus bar, through this switch, and out, so to complete the circuit. This coil would be melted in a small fraction of a second, I think, if it weren't very effectively cooled by water coming up from below and through the coil and out through these pipes that you see here. This magnet is used to measure the magnetic properties of very feebly magnetic substances. By connecting a specimen from the middle of the coil where the magnetic field is created through a fine wire or string, through this tube here, to this very sensitive microbalance that Mr. Lin is adjusting here, we can measure the very small force which even this strong magnetic field produces on relatively non-magnetic materials like copper, aluminum, oil, water, and so on. Here we have a second electromagnet, and back there a third one. And over here we have a couple of researchers connecting up the very last word in magnets as movable and efficient. As John has said, this movie is about magnetic forces, like the forces of attraction between these two permanent magnets and the forces of repulsion. These are the forces which drive all electric motors. We want to demonstrate in this film that magnetic forces are due to electric currents. This you can show perfectly well in your own classrooms and laboratories with very modest equipment. Since we have here, however, these big currents we want to use them to put on a new kind of demonstration that we've never seen ourselves. We're going to use the magnet laboratory just for having fun this time. In order to get the currents into these big bus bars, we have to turn on the big motor generator out there. We're going to take you out to have a look at it, and you might notice that very considerable forces are required to move the very heavy machines we have out there. Those are magnetic forces. Okay, Beans, you all set to fire it up?
Yes, sir.
This is the machinery that provides the current to the electromagnet. It consists of a motor operated by current from the power line and a generator, which provides the current for the magnet. I think the size of this apparatus gives you some feeling for the forces that are required to turn it over, and some feeling for the current that we will be using in these experiments.
The first thing we're going to want to show is something about the forces between currents. That's something we know about in the magnet lab, isn't it, Henry?
At least we're finding out rapidly. We sometimes try to generate very high magnetic fields for very short periods of time by putting very strong current pulses through small coils. We just cut open one here, which holds the world record right now.
Yes, the currents go around this way, don't they?
That's right.
No.
Of course, we've made many before this one which didn't hold up, and here's one that blew up. The conductors were forced outward, making it look like a barrel.
Well, here comes John. Now we want to show you something about the forces which currents and conductors exert on each other. These, in general, can be very complicated. In fact, if we wanted to describe the force on some little piece of conductor here due to the currents flowing in the whole thing, we'd have to take all the currents into account. Before we're through, we're going to have to consider the whole idea of a magnetic field to describe these forces. However, to begin with, let's take the simplest case possible of two parallel wires like this and examine the forces which they exert on each other.
The biggest problem I have with that is trying to remember which way the forces go. So we're going to demonstrate it in a way that I think makes remembering it easy. Here we have a bundle of parallel wires, all connected to a bus bar up at the top. Currents flow down through these wires, all in the same direction, and out through this copper strap to another bus bar over there. Okay, let's see what happens when we pass current through it.
All right, Beans, let's have a little juice here, and let's start gently. Let's have about 1,000 amps to begin with. Takes a minute to build this all up.
You want it on the telephone.
Oh, tell them to call me back later. I'm busy. How's it coming, Beans? You got 1,000? All right, let's go on up to 2,000. There we begin to go. 2,000. On up to 3. Let's show it really.
3.
Oh, there we go.
4. 5.
I guess that's enough. Let's cut it off. Well, I guess there isn't any argument about which way those forces are working. When currents are moving in the same direction, they attract each other, and you could see that by the squeezing up of this bundle of wire.
You've seen what happens when we have currents flowing in the same direction. This time we're going to see what happens when the currents flow in opposite directions. The current comes in from the bus bar through this flexible copper strap, down through this solid copper rod, and back up the other side, and out this flexible copper strap. Now these are solid copper rods. They don't move easily, and the current on one side goes that way, and on the other side goes this way. Now let's see what happens. You may fire when ready, Maestro.
Okay, Beans, this time I want you to set the equipment so that when you close the circuit breaker, you get the full output of the machine through these all at one crack, and stand by to open it up in case we get any trouble here. Okay, let's take it away. Yeah, there it is, going out.
There, you see how far it's spreading apart? Now those are solid copper rods.
There she goes. Whoa, shut it off.
Okay, fire's off.
Did you see the flash out there? That was a circuit breaker that opened the circuit when we were getting too much current through the machine. Okay, go ahead.
500, 1,000, 2,000, 4, 5.
Let's get going on the next experiment. You make the connections while I say a word.
Okay, I'll go get started.
This is a magnetic compass needle that's used to explore the field of the Earth. And we want now to use a compass needle like this, or a whole lot of them, to explore the field around a current.
Well, here we have a loop through which current comes in to these copper straps here, flows through this loop made of copper bars, out around this way and out through these copper straps to the bus bars. Now we're going to study the magnetic field due to current flowing in this copper rod. We're going to explore it with the help of all these compass needles here. Now right now they're all pointing approximately north and south due to the Earth's magnetic field. I say approximately because this is after all a magnet laboratory, and there are plenty of stray magnetic fields around here that are as big as, if not bigger than, the Earth's field. Okay, Beans, let's have about 1,500 amperes through the wire. And now you can begin to see some activity. They wiggle around and start to line up in the form of circles going right around the rod through which the current is flowing. All right, Beans, let's reverse the current now. We have to turn it off first and then reverse it. Now, you think you can see what's going to happen? We're going to turn around and point the other way. Now you can see they all point in circles around this way. Okay, Beams, that does it on the current. Cut it off. The lines of magnetic field are circles around the current, and they reverse direction when the current reverses.
Now we want to show you an experiment involving this good old lecture demonstration magnet, which isn't part of the magnet laboratory at all, really. We need to have a magnetic field, and we can get it here between the poles of this magnet very conveniently. I'll just turn it on. Oh, I better watch my watch. I get it magnetized so much I get sick of having it demagnetized. I have to get along with just setting it every time I see an electric clock. Well, now we have a magnetic field here, and there's a very simple little way of showing this with a few little nails. I think you can see that we have here a magnetic field going from this pole to this one. Now we want to talk about the forces on a current-carrying conductor in a magnetic field. In an earlier experiment, we showed you about the forces between currents. Now we want to leave out the notion of the other currents and really discuss just the force on the conductor in terms of the magnetic field which is present where the conductor is located. I'll put this in here, and we can pass a current through it, through the little mercury cups into which it's dipping by means of these wires, so that we'll have a current at right angles to this magnetic field. All right, let's turn this on. I think you saw that we had here a vertical force upward on this current-carrying conductor when it was at right angles to the field. And whenever you have a field like this, horizontal, with a conductor carrying current at right angles, we'll have a force at right angles to both, an upward force in this case. Magnetic fields are produced by electric currents. In a circular loop of wire of this kind, a circulating current will produce a magnetic field that goes through the wire. If we have a whole series of turns of this kind to form a cylindrical coil, the magnetic field will be driven in at one end and out of the other. This is, in effect, a cylindrical magnet, and we want to discuss whether we can describe the magnetic field produced by a magnetized iron bar of this kind in terms of currents. Clearly, we have strong magnetic effects of some kind, and the question is whether this must be described in terms of a new concept of poles in a piece of magnetized iron, or whether currents will do. If currents can be considered in this connection, they must, of course, be atomic currents, not macroscopic currents. There are no wires connected to this, and this is a problem for atomic theory. An atom may be thought of as having a positive nucleus and a cloud of negatively charged electrons around it. And if this cloud of electrons is rotating, it will produce a circulating current of this kind, and the field due to this current may be thought of as very much like the field due to a circulating current through the wire. It will drive flux or magnetic field through the atom. And if we have a lot of these side by side, they will all drive field through the individual atoms. And in a magnetized piece of iron slab of this kind, we may think of magnetized atoms as being lined up so that the currents are circulating in the same direction, and these circulating currents drive flux through the whole business and produce a field very much like that which is produced by the single circulating current in this wire. Now, if we take a lot of slabs of iron of this kind that are magnetized and put them together to form a cylindrical rod, we see that all the circulating currents of the individual atoms may be thought of as driving magnetic field through the whole magnetized bar and out of the other end, and producing an effect very much like that of a solenoid of this kind. Now, John has been setting up our last experiment, and we want to examine a little further the nature of this comparison. Now we want to show you in this last experiment a little bit more about the nature of this interaction of a current in a conductor with a magnetized magnet. That's what John's been setting up here.
Well, here we have a pair of electromagnets. They're coils of wire through which we can pass a current. Now, we've arranged these in such a way that the magnetic field due to this one is in the opposite direction as the magnetic field due to this one. And we shall detect the magnetic field at this point in the center by means of a compass needle.
So this turns out to be kind of a magnetic balance,
That's the idea. When we get them exactly balanced, there won't be any magnetic field right in the middle, so that the compass needle will show.
Well,
why don't you put on a little current through yours? We'll see what happens. So there we have current flowing through this one, a magnetic field attracting the compass needle. All right, now I'll turn mine on and see what we get. So far, just exactly nothing. So let's raise the current a little bit, give her a spin to get it off dead center.
Well, that looks as if yours, well,
now
just about balanced.
Mine's going to be stronger than yours now.
A little bit stronger.
Yeah, okay, so I'll back mine off a little bit and make it a fair game.
Now it's weaker.
Now, here we have a bar of iron. I'm going to put the bar of iron inside this magnet so that the iron will, as you know, become magnetized, and its magnetic field will add to that of the current. Oh, it looks like I'm winning this time. See what you can do.
I don't know.
Here.
Haven't got very much poop here, but I have an idea. What do you say if we try to connect up the old iron sides out here and see if we can put enough current through that copper winding to counterbalance what looks like currents flowing around that iron rod?
Okay.
There's one bus bar connected onto here through a couple of good straps. And there we are. I guess we're ready for a little juice.
Okay, here it comes. 1,000.
Lie ahead. Yeah, keep going, yeah. Oh, I guess we haven't made it yet. Oh, it's beginning to melt. Oh, we haven't made it yet. Okay, Beans, I think that's enough. Well, I guess we didn't have quite enough current there to really equal the magnetization of the iron. I suppose it's clear now that the magnetic effects of magnetized iron are stronger than anything we could produce by driving currents through those coils. How's this possible? It's because within each iron atom there are such strong circulating currents. Because in the iron rod we were able to line up these currents, and finally, because in the rod there are so very many atoms.